Good morning, everybody. I'm Antonio Palasciano, and today I would like to thank the organizer for giving me the opportunity of presenting this work on behalf of the ALICE collaboration. And today I will talk to you about charm fragmentation studies with the ALICE detector at the LHC. So let me introduce a bit the topic. Heavy-Flavour quarks, as we know, are excellent probe for testing the Quark-Gluon plasma, since they are produced in the very early stage of the collision, and they experience the full evolution of this hot dense medium. In particular, by studying Heavy-Flavour quarks in small system, provide a reference basically for understanding their interaction with the medium. By focusing the attention on smaller system in particular, we can get in proton-proton collision information, we can test perturbative QCD calculation. As well, we can constrain and validate fragmentation and hadronization models that try to describe the full evolution of the system, starting from the hard scattering to the final state of particles that are detected by our apparatus. Then, focusing the attention on proton-lead collision, we are interested in finding possible modification to the spectrum related to the presence of nuclear matter. In particular, this talk will focus the attention on Heavy-Flavour jet and Heavy-Flavour correlations. This measurement can provide additional information with respect to single particle studies. In fact, we can relate the production of the Heavy-Flavour quark to the full set and the fragmentation of the Heavy-Flavour quark to the full set of particles that are produced. This measurement have been taken by considering the ALICE apparatus. In particular, here I'm focusing the attention on the detectors that are involved actually in this analysis. And the first four, which are basically enclosed in the central barrel, are used for tracking and particle identification, whereas the last two that I mentioned here are basically used for trigger and centrality multiplicity estimation. So going to measurement, I would introduce the charm target jets measurement, and let me a bit talk about how they are reconstructed. So first, lambda C and D0 particle are reconstructed by considering these hadronic channels, and after that, the anti-KT algorithm in the fast jet implementation is run in order to have a correspondence one-to-one between each particle, each target particle, and the jet. That is, when we consider only charged particles for defining a jet. Then an invariant mass analysis technique is applied in order to extract the D0 and the lambda C jet row yield. In particular, on the right, you can see the sideband subtraction method in order to have yield that are related only on the signal. And then we correct our measurement by efficiency, of course, and removing the feed-down contributions. And finally, a two-dimensional unfolding technique is applied in order to simultaneously correct the parallel momentum fraction that is carried by D0 or lambda C and the transverse momentum of the charged jet. So by looking at the measurement, I'm showing here the production cross-section for the zero target jet in proton-proton collision in proton-proton collision at three different energies, 5, 7, and 13 TeV. You can see here from the plots that there is a similar trend between the collision energy, despite a different resolution parameter is considered here. For example, for 5 and 13, for 5 is 0.3, for 7 and 13 is 0.4. And also you can see that the POEG, there are also comparison between the prediction done by two implementation of POEG, so in the EV quark implementation and the dijet implementation. And we can say that the EV quark implementation will reproduce the data prediction. Also, we can see that in the small transverse momentum region, the central point of the POEG prediction are constantly below the data observation, but there is an improvement going at higher PT, where also the central point seems to be in agreement. Then if we consider the digest implementation of the POEG generator, we can see that the trend is slightly different because measurements are constantly above prediction are constantly above the data measurement, and also a different trend with respect to the Quark implementation is shown. Then the other measurement is I'm showing here is the parallel jet momentum fraction. In particular, once the direction of the trigger particle, in this case the d meson, is defined, and once the associated charged jet is completely defined, we can consider the projection of the momentum of the trigger particle in the direction of the jet. So here I'm showing the probability density versus the parallel jet momentum fraction, and you can see that a much softer fragmentation. A softer fragmentation is observed, a small transverse moment, a small parallel momentum fraction with respect to the POEG plus PTA6 prediction, and also we can and this happens especially for the low transverse momentum of both d mesons and the charged jet. On the right, instead, I'm showing the differential production cross section, and we can see that the POEG plus PTA6 prediction will reproduce the data observation. This is at large PT. Then the same measurement has been done with the lambda C particle, which have been tagged with the pi proton K0 short, and these have been measured with a limited precision actually, and you can see from the right plot that POEG plus PTA6 and PTA8 in the Monash tune fail in reproducing the data observation, especially for what concerns the I region of the parallel jet momentum fraction, where instead the soft QCD implementation of PTA8, including color reconnection mechanisms, succeed. Then another measurement that can help us in addressing the possible modification to the hadronization and the fragmentation is the radial displacement. In particular, the radial displacement is based on this variable, the radial distance, that basically wants to quantify the radial aperture, let's say, or better, the distance between the tagged charm particle and the direction of the jet. In particular, you can see from left to right the measurement done in D0, lambda C, and the ratio between lambda C and D0. In particular, in this case, there is no difference between the prediction done by the Monash tune and the soft QCD implementation that also seems to be are actually in agreement with the proton-proton results. And also this happens for the lambda C, but when we move to the ratio between the lambda C and D0 measurement, we get basically this discrepancy at large radial distances that in this, as you can see from this plot, is actually affected by large statistical fluctuation. In run 3, we hope to have a not so limited precision in order to better address what is going on and to describe this kind of phenomena. In particular, what we question about a possible dependence on this ratio of the radial distance, and also there is a hint of a production of the lambda C more displaced with respect to the direction of the axis, also with respect to a D0, for example. Then I can show you measurement of the zero tagged jets in a proton-lead collision. In particular, here on the left, there is the differential production cross-section compared with the scaled POEG plus PTA6 predictions. And the same feature that we have observed in proton-proton collision is present here. So an agreement that improves with the larger transverse momentum of the jet, of the charged jet. And also by comparing the proton-proton measurement with the proton-lead measurement, we can see that these are compatible within statistical uncertainties. One can also measure the nuclear modification factor, in this case for the zero target jets. And in particular, we can see how the nuclear modification factor is compatible with the unity within statistical uncertainty. So basically, there are no evidences of nuclear matter effects in this case. And also here in this plot, the nuclear modification factor in central lead-lead collision is shown, where you can see a strong suppression of the nuclear modification factor that actually is compatible to what it has been measured with the meson. Then the other measurement I would like to introduce are Heavy-Flavour electron jets. In particular, in proton lead, we want to understand if there are modifications to the shape or the spectrum of the Heavy-Flavour electron jets. And in particular, we want to understand if these effects are present, so the broadening and suppression of the jet. These two tests have been performed, for example, here, that you can show here. In particular, on the left, the nuclear modification factor as function of the jet cone size, so the resolution parameter of the jet. And you can see that the nuclear modification factor versus the transverse momentum jet are compatible within statistical uncertainty. So basically there is this quantity is not dependent on the jet resolution. And on the right, you can see the ratio between the cross-section computed with different resolution factor in proton-proton, proton-lead, and simulated by POEG plus PTI8. You can see that especially between 0 and 40, measurements are in agreement, whereas if we look at large PT, statistical uncertainties become higher, and also you can see how proton-proton prediction are quite far from the POEG plus PTI8 estimations. But this is not sufficient to claim any modification of the jet shape. And so basically we can state that there are no evident modification of the jet in small system. The other measurement that is useful for addressing fragmentation properties of the Heavy-Flavour quark are azimuthal correlations. In particular, with azimuthal correlation, we can relate the fragmentation of the Heavy-Flavour quark to in particular to the particles that are produced in the same event. In fact, we can study the event by means of the angular distributions between all the particles produced and the trigger particle. Also, you can say we can study the fragmentation of the not observed, not detected Heavy-Flavour quark, and we can understand something about the underlying event that actually are particles not correlated to the fragmentation of the charm. Also, we can provide with azimuthal correlation distributions a differential description of the jet shape and in terms of transverse momentum of associated particle. And we can also understand how the angular opening, for example, of the jet. In particular, by studying azimuthal correlation distribution in proton lead, we can spot the possible modification to the correlation shape that are actually induced by cold nuclear matter effects. Here, I'm showing the typical shape of the correlation distribution. So it generally features an near side that is made of particles that are correlated with the Heavy-Flavour quark that has been tagged. The away side, so particles correlated to the not tagged Heavy-Flavour quark, and the baseline, which is mainly composed of the underlying event, so particle not correlated. Well, let me introduce a bit the analysis. So first, we reconstruct the meson candidate by considering this hadronic channel. Then we identify the class of associated particles that basically are primary particles, so electrons, muons, protons, kaons, and pions. And we compute the two-dimensional correlation distribution in delta phi and delta eta. And then we perform, as we do for Heavy-Flavor jet, a sideband subtraction in order to have a correlation shape that is only related to the signal part of the signal. Then we correct these two-dimensional azimuthal correlation distributions through an event mixing technique in order to correct for the limited acceptance of the detector and spatial inhomogeneities. Then we apply reconstruction and tracking efficiency, of course. We, in this case, then we project on the delta phi axis, and then we correct for secondary particle contamination, namely particles coming from the decay of strange hadrons or coming from the interaction with the detector. And then we remove also the of course, the beauty feed down contribution. Here, after that, the azimuthal correlation shape, as I shown 2 slides before, are fitted with a generalized Gaussian with fixed mean at delta phi equals 0, a standard Gaussian at delta phi equal pi, and a constant term to reproduce the baseline. And we can provide an estimation of the features of the 2 peaks. So basically the yield and the width. So here I'm showing the comparison between proton-proton and proton-lead measurement at 5.02 TeV. We can see that the yields for both the near side and the away side seems to be quite compatible in the 2 systems. Whereas if we consider the widths of the 2 of the near side and the away side, slightly larger discrepancies are present. Which are present in general. Then we can state that the consistent value of the yield and peak are present between proton-proton and proton-lead collisions. And since the compatibility that we have observed also in the correlation shape and this measurement that I'm showing here, we can state that there is no significant impact of cold nuclear matter effects on the charm fragmentation with the current statistic. Then the same study has been performed versus centrality in proton-lead collision. And so by considering 3 different centrality classes, in particular, you can see that the correlation shape among the three sets is compatible, and also by looking at the experimental observable, so the yield and the width of the near side, we can see a good compatibility among the 3 collision systems. That and this is let's say, we can say that there is no apparent modification to the charm fragmentation when we go from by considering different centrality classes. Then azimuthal correlation distributions are computed also considering Heavy-Flavor electrons. In particular, electron sources are semi-leptonic decays of Heavy-Flavor hadrons, and we are interested in this kind. These are our signal. And then there are several background contributions. The most important are Dalitz decays of light neutral mesons and photoconversion in detector material. In particular, we start from the inclusive spectrum of electrons. So we build electron-hadron correlation distributions, and we perform some correction, event mixing and efficiency that are in common with the d-hadron analysis. And then we consider the contamination from secondary particles, hadrons, and non-Heavy-Flavor electrons. In particular, for example, the last 2 measurements, the last 2 contaminations are removed considering, in the first case, an hadron-hadron correlation distribution that is weighted by the hadron contamination estimated from this E over P distribution. And the non-Heavy-Flavor component instead is evaluated by considering this invariant mass technique. So we want to remove the photonic contribution by considering the subtraction from unlike sign pairs and like sign pairs. These contributions are removed from the inclusive spectrum, and so we can get the Heavy-Flavor hadron correlation distribution. Also in this case, distribution have been fitted, and in particular, in this case, we consider instead two generalized Gaussian. And here I'm showing the comparison with the PTI-8 Monte Carlo predictions. You can see that the shape is well reproduced by the generator. And also, if we look at the experimental observable, so the yields and the width of the distribution, we can say that the near side is very well reproduced by PITIA, and the situation is a bit worse for the away side because especially for low transverse momentum of associated particle, PITIA tends to overestimate the away side yield. Whereas if we consider the width, PITIA in any case overestimate the measurements, and the situation is slightly better for the away side, but only because of larger statistical uncertainties as well as systematic uncertainties. Then the last measure, so the last measurement I would like to show you is the azimuthal anisotropy for Heavy-Flavour electrons. In particular, once the azimuthal correlation distributions have been, of course, we are here in a the proton-led frame at 5.02 TeV. Once the azimuthal correlation distributions are computed for high multiplicity and low multiplicity, we subtract the low multiplicity from the high multiplicity correlation distributions in order to remove the jet-induced correlation peak, and then we fit the modulation with the Fourier decomposition in order to get the azimuthal anisotropy that is found to be different from zero with about 5 sigma of significance. And here I'm comparing the V2 of Heavy-Flavour electrons, so coming from Charm and Beauty, with other measurement of the V2. We can see that our measurement, Heavy-Flavour measurement, are compatible with the muons measurement, and also they are about half, yes, of charged particle measurement. But also there are some caveats because the pseudo-rapidity range that we are considering is quite different. There is still need of some Monte Carlo prediction in order to understand better what is going on here. We can imagine that there could be some QGP droplets, so final state effects, that determines the presence of a V2 different from zero. So coming to conclusion, I've shown Heavy-Flavour tagged jets, and we have seen that most of the theoretical predictions successfully describe the production cross-section. There is actually a software fragmentation in data with respect to what has been observed in the Monte Carlo predictions. And there are possible hints of modification to the hadronization that have been observed with the radial displacement, though with large statistical uncertainty. And we have observed that no modification are induced by cold nuclear matter effects on Heavy-Flavour tagged jets. Then, by studying azimuthal correlation distributions, we can state that there is a really negligible impact with of cold nuclear matter effects with the current statistics, and also I've shown you Heavy-Flavour electrons hadron azimuthal correlation distribution in proton-proton measurement, and how azimuthal correlation distributions have been used to estimate the anisotropic flow for Heavy-Flavour electrons. Thanks for the attention.
Okay, thank you, Antonio. So for fantastic timing. So is there any question on Zoom for Antonio? Very quiet on Zoom today. Okay. Maybe need to think about it. Any question from the room? Nobody? Oh, I can ask all my questions. That's great. Okay, so I can start then. Can you show the slide when you have the electron conversion? Yeah. 16, I think, or 17.
Sorry.
Yeah, that one with the over P. Yeah, this one. Okay. So how do you exactly select the electron from conversion in the material? Do you only do same sign subtraction, or do you have some geometric cut that you check the angle between the two particles and
yes, if I remember well, we consider this invariant mass analysis. So basically, we consider an electron and we couple the electron with all the other electrons in the set, and we consider like sign and unlike sign pairs. And then we have also a cut here at 0.14 here, but it's not what's needed. And then we can estimate which electrons comes from photo conversion or not. So basically, this is the only.
But this is implying that you have 3 electrons, right? You have like di-electron and one of them converts and then gives you a photon with 2 electrons. Because otherwise, if you have like E plus E minus, so did you check this method with the Z? Did you make an invariant mass of the Z boson, or you have enough statistics and check if you have same sign there?
No.
Okay. Because I would just think that for each electron, you would just take, you see there is another one which is the opposite sign, and you track them down to the vertex, and then you see if they're very small angle. And this is what we used to do also in CDF and the CB. Okay, so you just check the charge like this. Okay, interesting. Any comment? Okay. No. I had another question. Can you go back when you do the PID? Did you go back to the?
No, sorry.
Yeah, go back.
Oh, back.
Yes, sorry. Okay, here. No, here in the PLAD to PP, the other one, the previous slide. Yes, this one. Oh, yeah. Okay. So basically, here you are saying that the azimuthal correlations, basically you don't see any difference between proton and proton lead.
Yeah.
And but is it consistent, or so the proton is blue?
Yes,
Is the proton is blue?
And then red proton lead.
So it seems that yes, the heels is always like consistent, but then the peak width seems to reverse a bit. No, it's not always. You have much larger uncertainty there.
Yeah.
You comment on that, or is there no?
We need here we need larger statistics to at least to reduce the systematic uncertainties, because most of also the statistical uncertainty, for example, here.
Yeah, that one is huge, right? So.
Yeah.
But so you're planning to have more, to do with more data. Do you also is it
This
P-LED and LED P, or is it only one? You say P-LED, but it's P-LED and LED P. They're both directions.
Sorry, I didn't.
You say P-LED there, but do we have both? We have P-LED and LED P reversed, where they reverse the beams. These are both samples. Just one.
Just one of the two, I guess. It's very similar. The other.
So you double the statistic. Let's say you're not problem of statistics. You're using half of the sample. Okay. Right. No, it's just statistical. I was thinking. Okay. Any other comment?
What are the plans for doing lambda C hadron correlations or correlation of d meson or lambda C with identified particles like protons? I mean, do you plan to do them with this data or with run-free data?
So actually, there is we are trying to get lambda C hadron correlation with run2 data, but it's just to see if it is let's say we are just studying if it is feasible or not. And then with run 3, we plan, of course, to do lambda C with hadron correlation. That is possible. And then we plan also, it is possible to do also D meson with kaons, for example. And we plan to do this in run 3. And it will be really important to have lambda C over lambda C H correlations, since given that we have observed, also Mattia has shown us the difference in the hadronization, it will be useful to understand what happens for the fragmentation and if coalescence enters in the let's say in the fragmentation, how the shape of the distributions is modified with respect to the hadron correlation.
Okay, let's check again on Zoom. There is anybody in the meanwhile wants to ask something? No? One last question on slide 22. So you showed us the muon, is that the muons? Yes, the charged particle in blue, and then this the muons in these two directions, and so this account for about half of it. So what do you think is the other half? Is that when you see the electrons there? So is that just muon and electrons, or you check pions, kaons?
For charged particles, we include pions.
Okay, so you think that the difference is due to that? What I mean, did you check specifically, like you did with the muons and the electrons, each of them? No. Okay. Wait.
No, go ahead, Fabio. We are going to say the same.
Okay.
Yeah, but no, indeed. Yeah, we have muon. Okay, muons at forward backward rapidity, then electrons at mid rapidity. They are mainly from Heavy-Flavour. Muons from 2 GeV onwards, mainly from Heavy-Flavour. But what? No. Charge is inclusive. It's inclusive. Then of course we have measurements with the. In Pilet, no. It's inclusive. Yeah. To be taken into account that there's also different PT scale between the parton and the final trigger particle, so the charged particle or the Heavy-Flavour decay electron or muon, and there's also the decay kinematics from the duty charge hadron to the electron that enters in play. So an apple-to-apple comparison here without any model is difficult. Just
the separate, like you did for muons separately and then charged particle together, if you did the same for kaon and pion. No. Okay. Maybe with this announced PID probability that Mattia showed us. Okay,